Okay, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. Can you hear me?
Yes, Prof.
Okay, right. So today we will discuss on the chapter 4, mkem1763. The title is the parameter estimations. We already looked at the experimental planning, the input signals, okay, some analysis of correlations, and then we already looked at the model structure, okay, of the non-parametric and parametric models. And now is to go to the next procedure number 3, which is the parameter estimations. So basically, if you look at this block diagram, okay, so we are already go to the excitation signals. We see some input signals from PRBS, from sine wave, impulse, and step or square wave, okay, injected to the plant via to the computer, okay. So in the computer, we have A to D and D to A, which is the data logger system or data acquisition system. And this will be injected, the input will be injected to the plant, okay, as U, and then the output will be Y, and both will be captured using analog to digital converter. And the identifier algorithms here is the part that we are looking for, which consists of step-by-step procedures or protocol in calculating all the coefficients of the mathematical model. Okay, there's a lot of methods. Okay, so we will focus on 1 or 2 methods. Okay, because this method already implemented in the MATLAB programming in the function form, so you just call the function in order to estimate the parameters. But anyway, we have to learn some basics idea how these identifier algorithms will produce the mathematical model that we want to use. So it's come back to the what do you call that, the issues of analytical versus empirical. How do we obtain a transfer function via empirical? Okay, so if you the system basically is not stable or unstable systems, okay, due to the fact that the system have a poles on the right hand side of the S-plane, so it's not practical to apply empirical or experimental modeling to the unstable system. So usually we will go for the analytical method where we can see the gap that make the system unstable. That's why we can design a controller to make the system from unstable become stable. Okay, but for stable system, and we want to know the mathematical model. The system is stable but very complicated. A lot of higher order systems. So that's why we apply empiricals. Okay, empiricals modeling in order to obtain the approximate model that represent the system. But anyway, if you look at the Albert Einstein's their kind words, okay, any intelligent fool can make things bigger, more complex, and more violent. It takes a touch of genius and a lot of courage to move in the opposite directions. So I can say that empirical modeling is the opposite direction, or reverse modeling, okay, that try to give alternative way in order to do the mathematical modeling with the help from the computers and latest technology of A to D and D to A data collections, so we can get a good model. Okay, a good model is not obtained by accident, but requires careful planning and executions of the essential steps. So the steps must be correct, must be follow the standard of procedure, what to do first, what to do next, and so on. So that's why we do the setup, okay, for the system ID. Okay, you must have the excitation signals. That is important. You can design the hardware to produce the excitation signals, or you can simply do the programming. Okay, do the programming and simulate it and inject to the plant. Okay, the important thing now here is when you do data collections, the sampling must be right. Okay, the process must be ongoing and did not disturb the plant when the plant is running. Okay, that's why the procedures here is such a paradigm that we must look into step number 1 and step number 2 particularly, because when you do a wrong experimental planning without any protocol, without any procedure, so it will make the data that you collect is not the information that we want, okay, and it will not suitable to the model structure that we choose. So that's why model structure selection also important, okay, to see whether the system is linear, is it non-linear, is it minimum phase or non-minimum phase, and then is it the system is under the, what do you call that, parametric structure or non-parametric structure. And then finally, you will go to the estimations and validations. Step number 4 is the validation, just to verify and validate the model that we get, the coefficient that we get is correct, okay, by using some statistical testing, okay, for example, best fitting, for example, final prediction error, for example, IAC, and so on, okay, that will be discussed in chapter 5. So I give you an illustrative examples where if we have a simple motor, a DC motor, okay, connected to the power M, and we have the input Vi and we have the output V0. Okay, so the input, okay, is the step input, and the output is the motor, okay, the speed of the motor. So this motor will rotate. Okay, when we give a power supply, it will rotate, and the speed of the motor will be measured using a sensor. And the sensor is here, tachometer, right? So tachometer is the sensor that convert the rotational speed into the rotation of the RPM, that measure the RPM of the motor and then convert to the equivalent voltage, okay, V0, right? So we cannot use RPM as the output, since the when we to capture the data using a computer, so it must be converted into voltage or current. So that's why we use a tachometer, right? So the model structure is assumed to be a first order, okay, 1154 divided by S plus 33, okay. This is just assumptions, okay, examples for you. And then the data was sampling at 0.05 seconds, which is 50 milliseconds. And then it will be, this is a S domain, which is a continuous form, will be converted to the discrete form, okay? So is Q, okay? Q is the operator, or in other books, they use Z, okay? So it's similar, either Q or Z. And the input of the data is the step input, where we inject step, okay, at the input, and then we collect 3 data points by, okay, multiplications of the transfer function P and the U, the step U. Okay, so from here we use the power series expansion to obtain the three values of YKT. So this is data that we collect. Okay, at K is equal to 0, input U, input is 1 volt on the steps, and we produce the Y 0, and K equal to 1, the input is 1, is 3.77 volt, and then 2, the input is 1, and the voltage equivalent speed is 4.49. Of course, the speed will be higher at 4.49 compared to 3.77. So the issue now is we are going to estimate all these, what do you call that, the coefficients here, okay? Here, the one that I highlight, okay? This is the coefficient that we are interested to know the values in parameter estimations. So parameter estimations is actually an effort seeking to find the best values for a given parameterizations, okay, the best value, okay, and we have to select an appropriate cost functions to minimize it, which is high cost is not good, while the low cost is good, and this will apply optimizations, okay, standard optimizations problem in order to estimate the coefficients, we solve it. So the most popular one is the least square, okay, which is always being used in MATLAB software as a functions to estimate the coefficients of the parameter of the systems. So the term parameter estimations usually refers to the process of using a simple sample data to estimate the parameters of the selected model structure. And then several parameter estimation methods available currently. There's a lot of methods, okay? Start with the relative simple method of probability plotting and continue with the more sophisticated methods of rank regressions, which involve regressions. For example, a least square, maximum likelihood estimations, and Bayesian estimation method, and so on. So it will be here, okay, sorry. It will be here, the model that we are going to estimate, okay? Here. Use a pen here. Okay. This is the model that we're going to estimate, and we will compare with the real system, okay? For example, the DC motor just now. Then we will give the input, okay, to the real system and the same input to the model. So this one is the experimental part. This one is the simulation part, where this one is the actual one, okay, actual output, which is Y, and this one is the estimated output, okay, which is usually we do the notification as Y cap, okay. So Y and Y cap will be compared, okay, positive and negative will be compared, and you will produce an error, okay, and this error must be as small as possible because it will provide a quality factor to the estimation method that we use. The least square is over here, okay, least square, and least square will use the data of the input and output based on the quality factor, and then estimate the coefficients, and then update the estimated model that we're going to use, okay? So we call it as a block diagram of the parameter estimation identifications. So parameter estimation provides a mean of estimating the parameters directly from the data. So this is another block diagram, which is more simpler compared to the first one. Okay, so we compare the actual output and the estimated or predicted output. Then we will go to the error, and then actually the quality factor is over here, okay, in this line, okay, and then estimation goes to this line, and it will provide the estimated output, which is the function of the input, and beta, which is the error factor, or the coefficients of the system of the models. So parameter estimation applied in so many things, especially in the monitoring, machine learning, noise cancellations, vibrations, forecastings, and any predicted system that we're going to use. Okay, so this is some of the picture or the application of the parameter estimations. So back to the least square method that we are going to discuss, where least square method is the based on the data set composed of m desired input-output pairs, which is u and y. So we must have input data and we must have output data, which is represented by u and y. And I from 1 to m is the sequence, we call it as the training data. So system ID needs to do both structure and parameter identification repeatedly. Okay, so it's a looping process until satisfactory model is found, and it will do all this procedure. First is to specify and parameterize the class of mathematical models representing the system to be identified. The second one is to perform the parameter identification to choose the parameters that best fit the training data set. Third one is to conduct the validation set, okay, to see if the model identified respond correctly to an unseen data set, and then terminate the procedure once the results on validation tests are satisfactory. If not satisfactory, you have to repeat again the step number 2 and step number 4 again. So general form of least square estimate is represented by these statistics equations, okay, which is y is equal to theta f1 u plus theta 2 f2 u plus dot 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 plus theta n fn, okay, where u is the input vector, okay, the model input vector. F1 are known as the function of u, and theta 1 until theta 2 and theta n is known as the parameters to be estimated. And of course, y is the output. So the task of the fitting data using a linear model is referred to as the linear regressions. So you're going to apply your regressions, okay? So we collect a training data sets of the input, okay? And the equation previously in the slides, okay, in the slide previously, will becomes F1 in terms of U1 theta 1, F1 U2 theta 1, and F2 F1 UN theta 1, which is all this in the blue block color is equivalent to the equation A theta is equal to Y. So where A is a M times N matrix, okay, which is here in general form, and theta is the unknown parameter, which is theta, theta 1, theta 2, theta 3, and so on. So theta will be calculated. Okay, we will going to calculate theta using the least square method. And y is the output vector. So if we are A theta equal to y, so we can simplify these equations where theta is equal to inverse A, inverse matrix A multiplied by 1. That is the solutions for the theta. So we have m outputs and n fitting parameters to find the equations and the unknown variables. So usually m is greater than n, since the model is just approximations of the target system, and the data observed might be corrupted. So therefore, exact solution is not always possible. So to overcome these inherent conceptual problems, an error vector E is added, okay, to compensate the value, okay. So that is not run away, the difference between the actual and the real one is not give a high difference. Our goal now is to finding the theta hat, which is the estimated value that reduce the error between yi, the actual, and the estimated, okay, y and y cap. And then minimize it, okay, you have to minimize it, okay, using the given formula here. And then if E is equal to y minus a theta, then you have to rewrite the error E theta become the summations as shown here. And then we need to compute this, okay, using a computer and computer programming. So the theorem of least square, okay, said that the square area is minimized when theta is equal to theta cap. We call it as the least square estimators or LSE, which satisfy the normal equations here. A theta, A transpose, okay, A transpose multiplied by A, multiplied by theta cap equal to A transpose multiplied by Y, where A transpose A is a non-singular, okay? It's a non-singular matrix, and then theta cap is unique and is given by theta cap A transpose E, both are multiplied together, then find the inverse multiplied by A transpose multiplied by Y in order to find the theta estimated. For example, okay, the relationship is between the spring length and the force applied. So this is a simple examples, illustrative examples, where the equation is L is equal to K1F plus K0, which is a linear model, okay? So our goal is to find the theta cap, which is equal to K0 and K1 multiplied by T, that best fits the data for a given force. So we need to determine the corresponding spring length, which is L0. So the solution is we provide two pairs of data, okay, LF, L0, F0, and L1, F1, and solve a linear system of two equations and two variables, K1 and K0. So K1 cap and K0 cap. However, because of noisy data, this solution is not reliable. So we have to use a larger training set of data, which is solution number 2. So we do the experiment. Okay, so experiment 1, 2, 3, 4, 5, 6, 7. So this one no need data logger system. We just using manual measurements, okay, individual measurements where we give a force to the spring, okay, 1.1, 1.9 until 9.2, and then the spring will be, stretched in the 1.5 inch, 2.1 inch until 5.0 inch. Okay, so this is a training data for the spring examples. Okay, so what we do is since y, okay, is equal to E a theta, so we can write the equations here. Okay, 1.1, which is based on the data just now. Okay, 1.1, 1.9, until 9.2, sorry, multiplied by K0 and K1 plus E 1, 2, 3 until E7, because we have a 7 data, and the stretch in inch, okay, 1.5 until 5.0. Therefore, the least square estimate of the K0 and K1 multiplied by T, which minimize this equation, is equal to K hat, K0 hat, and K1 hat, the least square estimator, which is the A transpose A inverse multiplied by A transpose multiplied by Y, which is 1.2 and 0.44 respectively. So we rely on this estimation because if we have more data, but as you know that least square estimators also have the degree of freedom, which is shown here. Okay, L0, K0, K1F, K2F, and so on. And higher order models fit better the data, but they do not always reflect the inner law or the governance of the system. For example, if we increase the force, okay, from 9.2, so the maximum one, so we increase to 10, so the length will be decreased because the physical of the spring itself have a limit, okay? So it will not give the correct data as what we want. This is the visualizations of the polynomial estimations, okay? First order for the spring, first order polynomial for the springs. You can see that 7's data is replaced by the green point, okay, and the blue one is the least square estimator for first order. Okay, so A is not acceptable. Okay, B, second order polynomial, looks good. Okay, it looks good. Okay, but compared to the third order polynomials, it looks better. Okay, 2 and 3 is better, but 4 is out of options. Okay, so the best representation is either second or third order polynomial. So as an introductory examples, so we collect the data, okay, shown here, where k is the sequence number 0, 1, 2, 3, 4. So we have the length of data is 5, and the input is u and y, okay, as the output. Okay, so t is the sampling time, okay, of the computer that collect the data. So the hypothesis of the model structure for first order is shown here. Okay, so this is the model structure of the first order. Okay, so B1 Q over 1 plus A1 Q. So usually Q is, we use Z, okay? So it is the same thing, okay? So don't worry about it. So it is a Z, eh? You can use Z, you can use Q, okay, no problem. So our target is to find the B1 and the A1 parameters that fits the data. Base the data is here. Okay, must fit the data as shown here. Okay, the length of 5 data using a least square. So using a difference equations, okay, yk is equal to minus E1 yk minus 1 plus B1 uk minus 1. So we go to the parameterizations, okay, from k equal to 1 to 4. So we stack the equations, y1, y2, y3, y4, and then minus a1, y0, 2, 3, 0, 1, 2, 3 for b1 as well. And then it's equal to y, 0, 1, 2, 3, 4, and u, 0, 1, 2, 3, 4 multiplied by a1 and b1. So the equation here, y is equal to x theta. This is your y, and this is your x, and this is your theta. So this is our target, okay, to find the parameter of A1 and B1. So using the least square formula that I showed you before, okay, theta is equal to x transpose x inverse x transpose y. So you do the multiplications, okay, and then find the value, the n value, which is theta, which is minus 0.91, with respect to the A1 value, and 2.0 usually to the B1 value. Okay, so you have to do this using a calculator. Okay, using a calculator in order to find the value of A1 and B1. That is the first order. So we have another illustrative examples. Okay. Here, so we have about 10 data of U and Y. So the hypothesis of the second order data is shown here, B1Q plus B2Q squared, 1 minus A1Q plus A2Q squared. Okay, so the parameter under calculation is the B1, B2, A1, and A2. So we desire this value using a least square. So the difference equation for the second order system will be shown here, which is yk, A1 yk minus 1, minus A2 yk minus 2, plus B1 uk minus 1 plus B2 uk minus 2. So use the parameterization as first order. So going from k equal to 2 to 9. So we stack the equation as shown here, and the unknown values A1, A2, B1, and B2 as shown at the back of the equations. Then we apply the y is equal to x theta. So in the notes is A theta. So x and A is the same things. Then we find the x transpose. X transpose meaning interchange between the rows and column, which I will show you in the next samples. Okay. Then we multiply. Okay, x transpose and y. Then use the least square estimation. So we will get the equations here, which is theta is 1.9, 0.9, 0.0, and minus 0.04. So you can see that in the fourth order system is 4 by 4 matrix. So second order will produce a 4 by 4 matrix, so which take a longer time. Okay, so I usually use 2 by 2. Okay, for the test and for the exam, because that will consume what do you call that, logical time to be completed. Okay, compared to 4 by 4 as shown in these examples. And it comes to the model here where the A1, the B1, the A1, the B1, A2, and B2 inserted as the coefficients of the transfer functions. Right, so let's go to the here, okay, where you have the give examples here. So we do it together using a whiteboard. Given that the process model is of the form of yk b1 z minus 1 over 1 plus a1 z minus 1 and u. So u is the input, y is the output. Z is the Z operator in the discrete form transfer functions. So our target is to calculate and estimate the value of A1 and B1. So the data given here, okay, K is the sequence number, 1, 2, 3, 4. UK is the input, YK is the output, okay, with the value given there. So estimate the unknown parameters B1 and A1 using a simple least square. Okay, so you can see that given the process here. So as I showed you before, for first order system, so we have to rewrite the model in the form of y k plus 1 is equal to minus a1 yk plus b1 uk. So it comes from the transfer function just now. Okay, if you go to the transfer functions, which is y k b1 z minus 1 over 1 plus a1 z minus 1 u okay. Okay. So how you get the equation? You just cross multiply. Okay. Y k 1 plus e1 z minus 1 plus b1 z negative 1 and uk. Okay. So okay. So
But
yeah. Question.
Prof, first I have to multiply with z to the power
Yeah.
1, yeah,
Yeah.
before I cross multiply.
Yeah.
Okay.
Okay. So after you cross multiply, then we want to remove this z minus 1. Okay. We want to make it disappear from the equations. So that's why you have to put a delay here, k plus 1. Okay. So it will become 1 plus as the equation just now, which is yk plus 1. So this one will become okay, yk plus yk a1 z negative 1 b1 z negative 1 uk. Okay, so I open the equation first. I do it step by step. Okay. Okay. Then from there, okay, you will get the equations here. Y yk plus 1 is equal to minus a1 yk plus b1 uk. Okay, so we cannot have this z minus 1 in the equation. That's why we have to apply the equation yk plus 1 is equal to minus a1 yk plus b1 uk. So rewriting the model in the form here, okay, which is represented by y is equal to theta beta, okay, where beta is equal to a1 and b1, right? So therefore, using the equations y is the equation of k plus 1. Okay, let me y is equal to 4 minus 12 and minus 4. Okay, so it will come, where did I get this? Is from here. 4 minus 12 and minus 4, which is yk plus 1. 1 is, if k is equal to 1, so 1 plus 1 is equal to 2. So we collect data number y2, then k is equal to 2, 2 plus 1 is 3, so we collect y3, then k is equal to 3, 3 plus 1, so y4, so y4 is minus 4. So that's why, that's why we get this y matrices, okay, which is using these equations yk plus 1. And then for the theta, which is the combinations of a1 minus a1 and b1, okay. So minus a1 and b1, okay, we obtain from the is under estimation, which is a1 and b1. So we have to find minus yk from the table and positive uk. So minus yk is obtained from here. Okay, sorry. Okay, here yk minus, minus yk. So minus yk meaning minus positive 12, minus 12 here. Okay, then the next one is minus positive 4 is minus 4, okay, which is here, minus 4. Then minus y3, minus 12. Sorry, minus 12. So it become positive 12. So y3 is positive 12. Okay, because of this negative. And then plus uk. So uk, u1, u2, u3, you can take directly from the table. Okay, 1, minus 1, and minus 1. Okay, take directly and then put in the column of matrix, column 2, matrix theta, 1, -1, and -1. Okay. And then beta is under investigations. Okay, until here, everybody can follow?
Prof,
Yes.
why we choose just 3? Why? There's Y4. Why we didn't put Y4 also?
Because we have only the length of data is only 4. Okay, so when we use k plus 1, so when k is equal to 1, y2. When k is equal to 2, y3. And when k is equal to 3, y4. And k is equal
I
to
see.
4, y5. Y5 tak ada. There is no Wi-Fi. Wi-Fi is not available in the data. Okay.
I see.
The only Wi-Fi available is in your computer. Wi-Fi. Depends on the data, so you must be careful. Some data have a
Yes.
what do you call that? Length of data is 4 here, isn't it? Length of
Yeah.
data is 4. Okay. So in this case, some table have length of data 5. So now it's 4. Okay. So everybody okay? Okay, inshallah okay. Okay, if not okay, you have to try lah. Meaning that you try to what do you call that? Train yourself, right? The simple one. Okay. So the least square estimators say that you have to find the equations here. The estimation beta, meaning the estimation beta is what? Okay, beta is equal to A1, B1. Okay, so the estimation beta will become estimated beta will become A1 estimated, B1 estimated. Okay, and then the formula, which is shown just now, okay, is the here, okay, beta cap is equal to minus theta transpose theta inverse. So is a lot of process there. First you have to transpose. Okay, so what is the transpose of equations here? -4, -1, 12, -1. Okay. Moktaba.
Yes.
What is the transpose of this theta?
Will be the row will be the column. Every row will be the column. So -12, 1, -4, -1, 12, -1.
نعم. ممتاز. مبروك. إن شاء الله.
شكرا.
Yeah. Okay, so this is simple one by manual, but if the matrix become bigger, so you have to do computer programming. Right, so what is the size of this theta matrix? Alkali.
2 multiply 3.
2 multiply, no, not 2 multiply 3, it's 3 multiply 2.
No, I mean the transpose.
Yeah, the transpose is 2 multiply.
Yeah.
Okay. 2 row multiplied by column. Okay. Right. So that is the theta transpose. So you have to now is proceed, which is multiply of here multiplications. Okay. Theta transpose multiplied by theta. Okay. So theta transpose is 2 by 3. Okay. Then theta only is 3 by 2. Okay. Okay, so if we look at the values here, this one, okay, and then the transpose, minus, okay. Okay, so if you go here, I share. Okay, so if you want to multiply, this one is 2 by 3, this one is 3 by 2. Okay, so it looks to me is you can multiply this one, and you will produce 2 by 2, 2 by 2 matrix. Okay, so you multiply using a calculator. Okay, using a calculator, so you can multiply it. Okay, you can multiply, then you will get the value is 304 minus 20 minus 23. Okay, using a calculator. Then proceed to the next one, which is you have to find the inverse. Okay, inverse matrix of theta transpose theta. Okay, so how you're going to do it is you can do it manually. Okay, it's not that difficult. Inverse matrix. Okay, so inverse matrix is first adjoint.
Adjoint over the determinant.
Yeah, adjoint divided by the determinant. Okay. So if I look here, three zero four three. Okay. So it depends on the school of thought. So if you want to do it manually, this one change place, then positive. Okay. That is the adjoint for 2 by 2. Then the determinant is 304 multiplied by 3 minus 400. Okay, minus 20 is 400. Then you simplify. So you simplify, you will get the value of the transpose is here. Okay. Okay. And then multiply the transpose with y, okay, which is minus 48 and 20. So minus ty is okay. So y is y. Okay, y is 4 minus 12 minus 4, and theta transpose is minus 12 minus 4 and 12, 1 minus 1 minus 1. Okay. So for the last part, which is this one, so this is 2 by 3 and 3 by 1. Okay. So you will get your answer is the transpose y, which is 2 by 1. Okay. So theta transpose y is minus 4820. Minus 4820. Okay. So after you get everything, okay, which is theta transpose theta, then theta transpose theta inverse, then theta transpose y. So we multiply these three, combine it in the formula, and then you will get 0.5 and 10 as the value of the parameter first order. A1 0.5 and B1 equal to 10. Okay. So you insert the value inside the transfer function. B1 is equal to 10 and A1 is equal to 0.5. Okay. All right. And then using this formula, YK is you can calculate the actual value and fill up the form here. Okay. So what is the value for the table there, the estimated YK? The actual Y is 12, 4 minus 12 and minus 4. So in this case, if you want to calculate the value of the YK and to find the error, is you have to calculate manually, okay, using the formula here. If K is equal to 1, okay, Y, K plus 1, Y2 is equal to 0.5 A1 minus A1 multiplied YK, Y1 is 12. Okay, Y1 is 12 plus B1 is 10. Okay, multiplied by U. What is U? U1 is 1. So what is the value of Y2? Minus 6 plus 10. So it's equal to 4. Okay, so error 0. The next one is K is equal to 2. Okay, K is equal to 2. So Y will be Y3. Okay, same coefficients, 0.5 multiplied by Y2. Y2 is 4, right? Plus B1 is 10. Coefficients multiplied by UK, U2. U2 is minus. So what is the value here? Negative 2, negative 10, negative 12, negative 2. Okay, then error still 0. Okay, and then the next one is K is equal to 3. Okay, Y4. Okay, Y estimated 4, Y estimated. Okay, y4, which is minus 0.5 multiplied by y3. Y3 is minus 12 plus 10, the coefficients, multiplied by u3. u3 is minus 1. So it will become 6 minus 10, which is minus 4. So still 0. The error is 0. Okay? The average error also 0. 0 plus 0 plus 0 divided by 3 is 0. All right. So we have a time break. Okay, 10 minutes. Okay, 10 minutes break.
Okay.
Hello. Are you sleeping?
Okay. No.
Huh? Are you sleeping? I hope you're not sleeping. Okay, have a break for 10 minutes, right?
Okay, bro.
Okay, we continue our lecture by looking at these simple examples from the past year questions. Okay, so the difference is the value of the data is different. Okay, you can see that the value is different here. Okay, and but the model structure is still the same. So you can use this as a practice for you. Okay, after the class. Okay, to train yourself to estimate the value of A1 and B1 using the formula that I just showed you before. Okay, for the by rewriting the model structure. So disappear the Z minus 1 in the equations, then you can probably calculate, okay, the value of the estimated Y. Okay, so same things, use yk plus 1 is equal to minus a1 yk plus b1 uk, or y theta is equal to beta. Then identify the value of the y. So let's say here yk plus 1, so is one step ahead. So k is equal to 1. So you have to take data from y2, k is equal to 2, y3, k is equal to 4, k is equal to 3, y4. So you have to take y2, 3, and 4 from the table, which is 5, 0, minus 2. Okay, so 5, 0, minus 2, you insert in the column of the matrix Y. Then for theta, okay, so the theta is here. So it consists of positive and negative. Okay, positive and negative. Okay, so positive y, negative yk plus uk. So negative yk meaning 1, 2, 3, 4. Sorry, 1, 2, 3, because our output is 3. So you have to take data y 1, 2, and 3, and negative all. Okay, so negative all. So negative 4, 4 minus 5, 0. So 4 minus 5, 0 will be in the, will be in the first column. Okay, and then plus UK, so you can take directly from the table U1, U2, U3, so 1, 1, and minus 1. Okay, 1, 1, and minus 1. So you can see here that the input is like a PRBS, am I right? 1, 1, minus 1, 1. Okay, so it between that number, right? Then beta is equal to A1 and B1, which is unknown. Okay, so find the transpose of theta, interchange between rows and column, then find the product of the transpose multiplied by theta. So you get the 2 by 2 equation, then find the inverse, which is adjoint divided by determinant. Okay, so for 2 by 2 is very simple. You don't have to use calculator. You just take this number 3 and 41, change the seat. Okay, change the position. 3 go to 41, 41 go to 3, and then you negative this side of minus 1 and minus 1. So negative, negative 1, so become positive 1, positive 1. Then you can find the theta transpose y, and then you multiply together, so you will get the value, which is 0.55 and 2.55. Okay. Then, as usual, I usually ask my student to calculate the estimated, okay, y estimated 2, y estimated 3, and y estimated 4, with the value of k equal to 1, k equal to 2, and k equal to 3. Okay, then you get the value 4.7, you insert here, minus 0.25, you insert here, and then minus 2.5, sorry, minus 2.5 you get here. Then the error will be the difference between 5 and 4.7, 0.3, the difference between 0 and minus 0.25, 0.25, and the difference is 0.5, okay? modulus, error must be modulus. Mean that if the negative, the error is negative, you have to find the modulus so it becomes positive. And the mean square error is the average between these three values, 0.3 plus 0.25 plus 0.5 divided by 3. So you get the mean square error.
Prof, MSE, it's short from what?
Mean square error.
Ah, okay.
Then some extra for you to do, but I don't have the solutions. I just have the answers. Okay, so you just do the method that I showed before. Okay, and then do the conclusions here. Okay, by substitute back in the equations. Okay, so this one is for your perusal, slide 44. So least square, although is popular being used, okay, but this method also have the breakdown, mean drawback or disadvantage, okay, when it's under a non-linearities, okay, when there is a quantization problem and when the noise is high, which produce signal to noise ratio low, okay, so how do we recover this good fitting? Okay, ideal case it works, but when there is a certain stochastic part bigger than the deterministic part, so it will produce such things such as nonlinearities, quantization, and noise. So one way to improve the identification on the noise and quantization is we are using a filtered least square. Okay, so we have to do another step of calculations besides simple least square. So we apply some filtering, okay, and averaging, time domain, frequency domain, okay, and lots of data will help, of course, okay. So in exams and tests, I cannot give you length data 100, okay, because it will be very complicated. Okay? And some of the students will fail, okay, and they cannot do the exams, and the ambulance will come, bring the student to the hospital because the length data is 100. So that's why I limit to 4 or 5, okay, for your calculations, okay? You understand?
Yeah.
So we have, as a lecturer, we must tailor up what we want to ask the students as long as they understand the concepts, that's good. And later on, when they want to do a PhD, they will go for higher order and do some programming. That's okay because you don't have final exam during PhD, just the oral exam after 3 years. So we use a filtered least square. So we are using the same program, sorry, the same block diagram where we have excitation signals, usually PRBS. We have D to A and A to D. Then we have the models, then identify algorithm. Just we add here the filtering, the input and the output filter. Okay, add the algorithms. Okay, so that you get the final model. Okay, to overcome the nonlinearities problem that shown before. So filter least square usually represented by this. Okay, this is the ordinary one. So when you apply the filter least square, so it will become some notation here. Okay, like a ocean notations, which is it is different from the top because you multiply by the filter up and down. Okay, at the numerator and at the denominator. Okay. So what do we use this filter is iterative algorithms. It perform a least square identifications, use the obtained denominator and 1 for numerator, filter the input and output, perform the least square identification on the filter data, use the denominator and 1 for numerator, and repeat 3 to 5 until convergence. Okay. So the theory is like this. Okay. So you have the models here. Okay. So you don't have to about the derivations. Okay. As long as you know the steps is okay. Then you postulate the filter, then multiply by both sides. So the equation become A equal to B plus zeta. Then zeta is not a damping ratio, is a coefficient value. Then the filter will be input at the YF and at the UF. and you have to multiply with the output, with the filter, and the input with the filter. Okay. Then it will become this method after you apply filter, so it will become a generalized least square. Okay, which is longer compared to the first one before. So what you do is you find the theta and y using data from the simple least square. This is the as shown in the example before. Then you analyze the residuals, okay. Then you apply the filtering, okay. Then you filter the input and output in the steps, and then you do the least square again. Okay, if you look at the formula here, once you get the value of YF and UF, so you apply the least square again. Okay, but the command will become power of F, F meaning filtering. Okay, so go to the second step until it converges. Okay, go to the estimated value that you want. Okay, so this is the block diagram to describe the generalized least square. Okay, so we go to the examples here. Okay, so you are given xk, which is equal to b divided by 1 plus a uk, and yk is equal to xk plus zeta k. So uk is the input, yk is the output, and zeta k is the zero mean discrete white noise sequence. Okay, so data is given here. As usual, data is given here. So find a simple least square estimate for E and B. Okay, so the true value, this is considered as the prior knowledge. A is equal to 0.5 and B is equal to 8. So this is just our guidance. Okay, so that the value will be in this what do you call that tolerance at A and B shown here, and it gives you the filtering value at initial 0, which is 29.97 and minus 1.87. Okay, so first of all, we find the simple least square estimate of B, right? So as usual, we manipulate the transfer function shown before, yk plus 1 minus a yk plus buk. But now we have a noise, so plus zeta k plus 1, 1 plus a, z minus 1. Okay. So in matrix form, it will become y psi beta plus e. So this is the theta b, theta beta, and e is by this zeta. Okay. So from the matrix value here, so yk plus 1, so yk plus 1, so if k is equal to 1, so it will start from 2, 3, and 4. So it is 0, 9, 3. So that is the value for first column of y matrix output. Then for theta is minus a minus yk and positive uk. So just take from here y minus 16, 0, 9, put in the first column. Then minus 1, 1, and 1, put at the second column. All right. Then beta, you leave it as what do you call that? The value that we are going to estimate, which is in this model. Okay, A and B. Okay. So and the least square estimated is given by here. Okay. So of course you have to remember this formula, brother and sisters. Please remember this formula. And it's not given in the exams and the tests, right? So find the theta transpose multiplied by theta, okay, which is a 2 by 2 matrix here. Then find the adjoint and determinant so that we can calculate the inverse matrix. Then calculate the output, theta transpose y. Then the 3 items above you multiply together. Then you will get the estimated value of A and B, which is 0.56. and 8.72, which is not far away from the true parameters value. Okay, the true parameters value is 0.5 and 8. The one that we got is 0.56 and 8.72. Okay, so you can calculate the error, the predictions and the real value. The real value is 0.5 and 8. The estimated value or the predicted value is 0.56 and 8.72. So now we are going to apply the second one, which is the generalized least square. Okay, so in generalized least square, you have to look here. Okay, yk. Okay, the formula will become y filtering k is equal to yk 1 plus a estimate. This a estimate is come from the value previously, which is 0.56. Okay, use the value that we get in the part 1, 0.56. Then ufk, the filtering part of the input is uk divided by 1 plus a estimate z minus 1. So this one also 0.56, the value that we obtained from part 1. So part 1 must be used, the value will be used. So a cap, okay, is the least square estimate of parameters A. Then you substitute into equation 1, give the generalized least square formulations, will become y filtering k plus 1. So it becomes minus a y f k plus b u of k plus the noise part here. Okay. Then you simplify, so it will become like this. Okay. So if a cap is equal to a, the simple least square estimate will be unbiased. Okay. Will be unbiased. All right. So using equation 1, we compute the filtered input and output sequence using the filter. So y fk minus e k minus 1 plus yk. Okay, for the filtering part. Okay, so the initial value given, y filtered 29.97. So start with 1, k equal to 1. So minus 16. Okay, minus 0.5, 29.97. Well, where do I get minus 16? Is from the table. Yeah, minus 16. Okay. This is from a cap. 29.97 is the initial value, zeros. So we'll get minus 32.78. Then y filtering 2, which is 0. 0 we get from here. After minus 16 is 0. So 0 minus a cap 0.56 minus 32.78. Use the previous value, which is yf1. We'll go into here, not 29.97. Okay, use the latest value, minus 32.78. Then you will get 18.356. Then continue, yf3, 9. 9 we get from the table here, y3. Okay, minus 0.56, the estimated A, 18.356. Okay, 18.356 is the yf2 value. So you perform the calculation, minus 1.279. Then yf4. So yf4 is 3. Okay, so where do I get 3 value? From here, table y4. Okay, so y3 minus 0.56 e cap minus 1.279 from the yf3 value, then you get 3.7166. That is the for output filtering. The input filtering also must be used here. So in this case, UFK, okay, is minus ECAT UFK minus 1 plus UK. So the value of the filtering initial is minus 1.87 given. Okay, then the value of UF is from minus 1 is from the table here, minus 1, okay, insert into here, so you will get minus 1, minus 0.56 is the A cap, minus 1.87 is given at UF0, so you get 0.049. Same as the output, so this value will go to here. This value will go to here, and this value will go to the next one. Okay, so minus 0.56 is constant from the beginning to the end, but 1, minus 1, 1, 1, and 1, you get it from the table here. Okay, so table is very important. Please refer to the table. Then you will get the UF value from 1 to 4. Same to YF value from 1 to 4. And this one will be sorted together in the new table. Okay, so this is the original one, UK, YK is the original one. Then the filtering one will be the one that you calculate before. Okay, 8 times. 4 for the input filtering, 4 for the output filtering. Okay, then from here, you apply the least square. Okay, which is the formula that shown here. Where is it? The least square, where is it? Yeah, this one. Okay, this one, right? The formula will be applied, okay, to the least squares. Okay, so the difference is we use F. Okay, power of F stands for filtering. So YF is 18, 3.56, which is on this part. Okay, one step ahead because YK plus 1. Then theta F is the minus YK plus UK. Okay, so in this case, minus 32, 32.78, minus 18.356, minus 18.356, minus 1.279, so it will become 1.279 because the equation has minus YK. Then plus UK, so UK directly from here, put in the second column. Then find the transpose for this, okay? Transpose for this, right? Then after that, you multiply with the theta filtering. You get 2 by 2. Then you find the inverse, as usual, like a simple least square. Then you multiply the output, simple, as a simple least square. Then this, you multiply together, okay? You multiply together overall, okay? You multiply together using your calculator, then you will get 0.58 and 8.5. Compared to the simple least square, 0.56, 8.72. This one you get 0.54, 8.5, which is an improvement on the simple least square estimate. Although the generalized least square solution after one iteration is still biased, but for the iterations will result in unbiased estimated or beta. So it will do the calculation. If you want to do a longer calculation, so you will calculate, okay, until you get the convergence of that particular value using a computer program. But for manually, you have to follow my examples here, my samples here, which can be calculated between half an hour to 45 minutes.
Prof?
Yeah.
So for the next step, if I want to get the more convergence, so the initial value of the filter of the output and input will be the last value from the previous step.
Yeah. Yes. Like this. It goes here. Okay. It goes here. This one is goes here. Then you can add Y, F5, and so on if the data is so.
I mean for the next step.
Yeah.
After this one.
Yeah.
If I want to get more conversions, the best conversions.
Yeah.
So the first value for the filter will be the last value here, which
Correct.
is
Yeah,
the Y4.
Yeah, correct.
Okay.
Is the looping method now? Is the looping? Okay.
Yeah. Okay.
So I give you some examples for you to try. Okay. This one is similar to the sample 2, which is just now. Okay, where you have a k is equal to 1, 2, 3, 4. Okay, yk is equal. It is a PRBI signal. Right? You can see that 1, 1 minus 1. And then yk minus 4, 5, 0, and 2. So the data is different, the question is the same. And the initial value is not 0 anymore. It is 6.255 and minus 2.0 as the initial conditions of the filtering value. I don't have the solution, so I leave it to you for you to try. Okay, for the answers given, which is shown in the slide 58. So any questions on assignments? Is there any question on the assignments? If you want to ask, you can ask now. Any question on the assignments? So the exams, so the test 2 will be on next week, 6th of January. Hello? Hello?
Yes, Prof.
6th of January.
Okay.
Okay.
So for the assignment,
6th of January, scope of test 2 is chapter 4 only. Hello?
hello, yes.
Okay, Prof.
Yes.
Four.
Okay.
4 only, parameter estimations.
Okay.
That is the course learning outcome number 2. Test 1 is course learning outcome number 1. Test 1. Test 2, we will test you on the course learning outcome number 2. Assignment, we will test both course learning outcome number 3, which is integration between system ID and estimation values. Okay, I open the class for any questions on the what do you call that? On the assignments, because assignment is 30%. Okay, any question?
Prof, for the assignment,
Yeah, name
Saravana,
Saravanan from
Bahawal Ismail.
okay, Bahawal Bismillah.
Prof, for the assignment, we have to do the second order system, right?
Yeah.
And the value for the inductance and the resistance and the capacitance, we have to select the random one, or we have to refer to the attachment.
You can choose RLC so that it will give you the second order type of being assigned. What is your second order type?
Series circuit as a second order.
No. The second order type, is it undamped, underdamped, overdamped, or critical damped?
Mine is under them.
Underdamped meaning your zeta is between 0 and 1. So you can choose any value that produce zeta between 0 and 1.
Oh, okay. So my second order system must be between the, I mean, the value for the resistance and inductance, right?
Yeah.
So I can select a random value, or I have to prefer. I mean, I have to based on the under them the system.
You can choose any values as long as it can be simulate and can be experiment and available in the market. So what is the model structure, Saravanan, for the second order?
For the second order, square.
Okay. So in terms of RLC, do you have the RLC formulated in your notes? I can't remember.
Yeah.
Do you have the, what do you call that? The samples that I give to you.
Yeah.
Can you please read for me?
Yeah.
In terms of R, L, and C.
RLC is
Then
one.
one.
The transfer function, right, sir?
Yeah.
1 over LC
Over.
over S square plus in bracket R over L S plus 1 over LC. Yeah.
Now you have to choose the R, the L, and the C.
Yeah.
So that this zeta
Okay.
between 0 and 1.
Oh, okay.
So you have to derive first lah. Derive this transfer function first.
Okay.
Inshallah, you can do it. I know you can do it. Okay.
So I have to do a derivation and
You
find.
can choose any value, random value, but at the end, if you want to use the test on the hardware,
Okay.
so the value must be available in the shop for R, L, and C.
Okay.
Faham tak? Cara, the way that you choose the value of R, L, and C.
Okay.
Any question from the floor?
Prof,
Yeah.
how about undem system?
And
Does
then,
it mean resistor to be zero?
and then, hello,
Yes.
brother. Hello. And then is zeta equal to 0. So in this case, your transfer function now will become okay. So this part is 0. So it will become n. Okay, and then you have to compare with this one, 1 over LC. It seems that there is no resistor, just LC.
Okay.
Correct. Huh?
Understand, bro.
Faham tak? Macam tak ada LC kan? Because this part dah 0 kan? This part is 0, so no need lah. LC only. Okay. As long as you get the undemp is equal to 0. So you want to see what happened by simulation and by experiment. At least you appreciate this assignment because we are online version. Okay, I try to give easy one for you to explore. Okay.
Okay, thank you, bro.
Any question? So for next week, we start with class first, okay? Then after about 1.5 hours, then we will go for the test one. As usual, go to the e-learning, okay? As usual, go to e-learning, then you open it, okay, and then you have to on your video, okay, as usual, then submit, okay, your test, okay, PDF versions. So you have to combine the cover, the plagiarism form, and the answers together, okay, compile together, become one PDF file. Then you submit, okay. You can use cam scanner handphone. You install cam scanner, much easy. Most of my students install cam scanner. So they scan one by one, then they merge together, okay, in one file. So I limit the test to for chapter 4 only, okay, because parameter estimations is course learning outcome number 2, and assignment is course learning outcome number 3. We already finished course learning outcome number 1, so test 1 still ongoing marking, so please be patient, okay. We have about 1 month from now to finish our chapter, okay. So the last one will be chapter 5. So next week, please install MATLAB in your desktop, okay. And please make sure you have a system ID toolbox. Hello? Hello?
Yes, Prof. Okay.
You must have a system ID toolbox, okay, together with you so that I can show you and teach you how to use the system ID toolbox, okay?
Okay, okay. Thank you, Prof.
Okay.
Prof, I have a question regarding to the assignments for the in the designing the PRPS. So can I can use anyone like D flip flop or JK flip flop? I can choose anyone, yeah.
No problem, as long as it's the register, okay?
Yeah. Okay.
Register. It's up
Okay.
to you, your design. So I will measure your design, your own design. Please show your creativity, okay?
Okay.
I will judge you on your initiative, on your effort, and on your creativity and originality.
Okay.
And of course, the discussion matters. No discussion, just figure, no marks. Yeah? Some
Okay.
students like, okay, the results, okay, shown in figure 1. Then come the figure, okay. Then no discussion. So no discussion, just a figure without discussion, okay. So the student maybe they want me to comment on it. So you have to comment because this is your assignment. So you have to write a few words, right?
Yeah, of course.
Write a few words,
Okay.
okay, and then your report will be in PowerPoint,
Okay.
because you are going to present at the end of the January. Okay, all of you will present to me during the class. Okay, during the class, so that I will ask question from your design. And then please take video from your hardware. Okay, take a video, short video, so that I can see your design. All right, so it's 10 to 4. Any question? No question? Al-Kali? Where's our Nigerian brother? Al-Kali?
Yes, yes, Prof. I'm together with you.
You are very quiet today. You just wake up from sleep, isn't it?
Yes. I joined very lately.
Okay.
My internet. Yes.
Okay, all right. So the notes is there. The link of YouTube will be sent to you.
Yes.
Okay.
Thank you very much, Prof.
Any problem on the assignment? Okay.
No more problem yet.
Inshallah, okay.
Inshallah, okay.
All the documents supported, okay. So try your best. Okay.
Okay, thank you.
Okay.
Thank you, Prof.
If there is no problem, so we ended our class here. So please read chapter 5, the slide that I give to you. The data will be given during WhatsApp. Okay. Thank you very much. Okay, and wait for my YouTube link.
Thank you, Prof.
Assalamu alaikum.
Salam.
Wa alaikum assalam.